and in this video we're going to focus on the two-sample t-test. If you've not yet watched the video on one sample t-test, please go back and do so. You're going to need that foundational knowledge in order to understand what we're discussing in this particular video. So for the one sample t-test, it's useful to evaluate if our mean is different from some type of hypothesized value. But in many situations, we're interested in comparing two different populations or two different treatments, maybe different ecosystems, different years, different species, different age classes. And so we can adapt the t-test to account for these two samples that we're interested in. And we have a slightly different formula, but the concept is the same. And this application can be used for two different populations, or it could be used to test across different years, different seasons, different ecosystems, lots of different questions that can be addressed. Now, the formulas that we're using to test these are going to vary according to the conditions of variance of the two samples. So if we go back to our assumptions of the t-tests, one of those was equal variance. Now, equal variance is just one of the potential situations that we can have for a two-sample t-test. So if we've got two different samples, we may have two samples that have equal variances, equal variability in their data. But this is pretty unlikely. And so in this particular class, we're going to make the assumption that our samples have unequal variances. And the reason for this is that the data are likely to vary from sample to sample, and so variance is highly unlikely to be equal across a particular situation. This is also going to provide us with a bit more straightforward formula in which to use. And so for this particular class, we're just going to focus on situations when our variances for the two samples are different. And so we can use this two-sample t-test to look at the difference between the means of two different samples. And so we can look at differences in lengths, differences in ages, differences in weights, lots of different potential factors we can investigate across two different samples. Now, as with the single sample t-test, the one sample t-test, we have a variety of options for our potential alternative hypotheses, either that the means are unequal to each other or that one mean is greater than the other. But regardless of what our alternative hypothesis is, our null hypothesis will always be that the two means are equal. And what this means is that the difference between these two means will equal 0. And as we'll see in a minute with the formula for this two-sample t-test, this will give us a test statistic of 0, which will never be greater than the critical value that we're testing against to determine if we should support or reject our null hypothesis. Now, something important to note here is that we're denoting the different samples with subscripts. This is going to be important moving forward, so that way we can keep track of which values are related to which samples. For this two-sample t-test, it may be less critical, but as we move forward into some of the other statistical tests, keeping track of which sample has which data is going to be really important. So our formula for this two-sample t-test is as follows. So it's the difference between our two sample means divided by the square root of the variance divided by the sample size for each one of our respective samples. And we take the summation of them before we take the square root, following orders of operations. So let's look through an example. Let's see how this actually works. So let's say that we're interested in Atlantic croaker, and we want to know if the weight of males is different than that of females. And so we know that we are asking a question about the mean of these samples, of these populations of organisms. And so we know that we're going to use a t-test at this point, and we know that we're interested in two different populations, males and females. And so we know that we're going to use a two-sample t-test. So we've got our null hypothesis in which the two means are equal. Now in this particular case, again, there's no context clue as to whether there is one particular sex that is larger than the other. using the information from the word problem. So our alternative hypothesis is that the two means are not going to be equal. And so this is going to dictate that we use a two-tailed test instead of a one-tailed test. And this will again affect our critical value. So we might have some data and calculate out the appropriate information, or we might be given some summary statistics here as in the table. And then we can use the information to populate our formula. So we have our means here, we've got our standard deviations, and then we've got our sample sizes. Now, in this particular case, it doesn't matter which of our populations, males or females, are 1 or 2. What's most important is that we're being consistent with keeping either males as our population 1 or females as our population 2. So we can populate our respective formula here and get our test statistic. Now, we have a negative value here, and we're going to talk about this in a minute, but if you feel uncomfortable getting negative values for test statistics for this two-sample t-test, I would suggest putting the larger mean as our sample population 1 and the smaller value for the population 2. Now for our degrees of freedom, we use the same formula here. It's n minus 1, but in this case we've got two different values for n. And so in being conservative in our statistical approaches, we're going to use the smaller sample size. In this case it's males, and so our degrees of freedom in this case is 17 minus 1. Now we can go to the same t-table as we did for the one sample t-test. We find our degrees of freedom, and we find our appropriate column for our significance level. Again, our default is 0.05, and this is a two-tail test because we're interested in both the left side and the right side of the curve. And we can use this to find our critical value, which is 2.12. We then compare our test statistic to this critical value and then determine if we should either reject or fail to reject the null hypothesis. Now we've got this negative number on the table. There's no negative numbers. The lowest number is 0. So this might be discouraging, but if we think back to several lectures ago, we know that these distributions are bell-shaped. They're equivalent on both the right side and the left side of the curve. And so if we have a negative t-value, it's the same as if we have a positive value in its place. So rather than comparing the critical value to this negative number, which of course the negative number will be lower than that, we compare it to the absolute value of the test statistic. So in this case, 1.245. So what we find is that our test statistic is less than the critical value, so we're going to fail to reject the null hypothesis. So there's no difference between the weight of female croakers and male croakers in this particular example. Okay, let's look at another example here. So we know that as animals get bigger, they're typically going to eat more because they have higher energetic demands overall. And so we can measure how much they're eating by weighing the amount of food that they've ingested in their stomachs. In this particular example, we're interested in determining if the bull sharks in Galveston Bay eat the same amount of food when they're age 0 versus age 1. So based on the word problem, again, we know that we're interested in the mean differences, so we know that we're going to use a t-test. We've got two different age classes, so we're going to use the two-sample t-test. We've got our formula here. And in this particular case, I'm going to adjust our subscript. So right now we've got samples 1 and 2. I'm going to switch this to 0 and 1 because then this matches up with our age 0 and our age 1. So our question then will dictate our alternative hypothesis. Again, we always have our null hypothesis that the two populations are equal. So our question is, are they consuming the same amount of food? But the information from the word problem indicates that as animals get larger, they should be eating more food. So in this particular case, we're going to choose this one-tailed test in which the population 1, the mean of what they're eating, should be greater, or we're testing if it will be greater than that of the sharks in age class 0. So we get some information here, our descriptive statistics, and we can use this to populate the formula. So take a moment, pause the video now, and enter those values into our respective formula. Okay, so we can take our data, we can put it into our formula to calculate our test statistic. Again, in this particular case, we're getting a negative value, but it's equivalent to the positive value if we had switched which of these populations was 0 and which one was 1. Now we need to determine what our degrees of freedom are. Again, we'll use the smaller sample size, in this case the age 1 sharks. So our degrees of freedom will be 28 minus 1. And then we can go to our t-table and find our critical value. Again, using our degrees of freedom, using our significance level at the respective one-tail column. We then find that our critical value is 1.703. Again, our test statistic is negative 1.987, but this is equivalent to 1.987, so we're going to take the absolute value of this, and what we find is that our test statistic is greater than our critical value. So we're going to reject the null hypothesis that they eat the same amount of food, and what this is indicating is that the age 1 sharks actually eat more than the age 0 sharks. Now, this example illustrates the importance of being able to determine if a t-test is a one-tailed test or a two-tailed test. In the event that we made the mistake and thought this was a two-tailed test, our critical value would increase from 1.703 to 2.052. And in this particular case, our test statistic would not exceed this critical value, and we would not reject the null hypothesis. We wouldn't have enough support. And so it's important as we move forward not only to be able to calculate these test statistics and to use the t-table to get the critical value, it's important to determine if we have a one-tailed test or a two-tailed test based on the information that we're giving and the question of interest. So we're going to spend time in class going through these one-tailed tests and two-tailed tests, and these one-sample t-tests and these two-sample t-tests, but it would be very good for you to go back through these videos, make sure you feel comfortable with the examples, and then also go to the text section 10.1 and practice exercises 10.1 to 10.4 in order to get extra practice and feel comfortable in conducting these t-tests. So this is the end of our videos on t-tests. A couple important things that you should be aware of and know is when to use a one-sample t-test versus a two-sample t-test to determine if the test is one-tailed or two-tailed, and then in turn how to identify what the critical value is for the test, and then how to determine if the means are different from one another or not, or how to determine if the mean is different than the hypothesized value or not, how to actually evaluate your test statistic versus the critical value. The next video is going to focus on a new test. It's going to focus on variance rather than on means, and this is going to be the F test.